So good afternoon. My name is Luis Benet. He's David Sanders. You already know him. We are actually both in Mexico, in the National University of Mexico, though David is actually at Julia Group here in MIT for a sabbatical year. So, not responding. Anyway. So what we will be describing are some applications of some notions of integrations of differential equations and other treatment on numerics in dynamical systems. And I will begin, so these will be the libraries we will be using actually: Taylor series, validated numerics, and forward diff. And on the way, we will be showing that there is a huge positive thing because Julia just allows everything to compose very nicely. So let me begin with the calculating the equilibrium points of the restricted three-body problem, which is already known since the 18th century or even before. So what's the idea? We have two massive bodies which are rotating on a circular orbit, two suns. And there is a third particle which has no mass and feels the gravitational attraction of those two. So the question is, what are the equilibrium points? These are the equations of motion, which I will not go into the details. And, well, these will be the constants. And here we have implemented all those equations in some way. So what we are going to do, it is use intervals to actually bound the location of those equilibrium solutions. So this is the main function to do that. The results are somewhere here. Is everything run? Well, I think I will have to run everything.
Oh, just try.
Go. Yeah. Okay. No.
Nothing's appearing.
Now it's there. Okay. So what you're seeing here, it is the initial box in a rotating frame, and these two guys are the stars that we will actually look for, that are moving on a circular orbit. And what I will be shifting is actually the size of the box. So the first thing that you do is that you try with this box, and you find that there is a zero inside. So what do? You simply bifurcate it in every direction. And then you get this bunch. It is absolutely not possible to see it. Can you see it? Anyway. Yeah, there you can see it. So what I have done, it is bifurcate. I get a bunch of new boxes that a priori contain the zero of the of the equations defining the fixed points. I go further in detail, and I get these darker boxes, further, and so on. And then you get, the usual places. So it seems that we have actually hit what we were looking for. So can we do much better? What I will be now doing, it is simply using Newton's method, but for intervals. I didn't emphasize that before, but everything here has been using intervals. And let me now here show the first guy which comes to the party. It is from Jared's package forward diff. We will be using the Jacobian. And notice that we're inverting the Jacobian over intervals. So we're also using some generic linear algebra there. So what do we get? Simply, well, these are the examples. So forward with diff actually works. These are the results of some intervals. The inverse also works. And at the end of the day, you get the Lagrangian 5 equilibrium points. So now we're sharing the stage.
So what are these intervals that we're using? So an interval is just what it says. It's a set of real numbers between a lower bound A and an upper bound B. And those A and B, we're going to use floating point numbers. So normally we would just use standard Julia float 64s, but you can also use big floats, or you can also use double or Jeffrey's extended precision floats that we saw yesterday. And so these intervals are provided by our package called validatednumerics.jl. So the title validated numerics, the name of the package, refers to the fact that when we do calculations with these intervals, as Luis just showed, those boxes are actually a rigorous, mathematically rigorous statement. So the boxes that we showed, basically, where there is a box, so let's say, where there is no box, we have rigorously excluded that region. We know it's a theorem that there is no zero inside that box. So how does this interval arithmetic work? So we actually presented this, I presented this last year, but since then the package has matured a lot. So it's, of course, as we've been hearing, Julia turns out to be a perfect, I don't know about perfect, a very, very good language for implementing this interval arithmetic. And of course, well, this is a field that has actually been around for 50 years, but it's still pretty difficult to use in the sense that there is, you know, there are lots of interval arithmetic packages, but they're all in C++ or in, they're difficult to use. So there's a recent one that I should mention in Octave, actually, which has provided some inspiration for our package by Oliver Heinrich. And but now we can do it in Julia, which has the usual advantages of speed, beauty, and all this composability that we're talking about. So as it was mentioned, I'm on sabbatical at MIT in the Julia group, and I would say that the main message that I have been learning over the last few months is the importance of composability and the fact that Julia does it so well. So we're going to actually see that in a really clear, hopefully, example about how we can. So the whole theme of the topic is so what do we mean by rigorous calculations? We mean how can we trust our numerics? How can we guarantee in a mathematically rigorous way so that each calculation with floating point numbers, which everybody usually thinks of as being these magical quantities that it's difficult to work with and difficult to know if you've made a mistake or if there's some rounding error that got propagated through your calculation. Interval arithmetic allows you to control all of that. And so it literally gives you bounds, upper and lower bounds, that you know are guaranteed to be correct if your package is programmed correctly. So in our package, we have this interval type. So here we're just creating an interval between 0 and 0.5, and we're calling it I. And, oops, sorry. Oh, come on. Yeah, so there's some issues going on with I don't know what's going on. Okay, so if we have two intervals, A and B, we want to define what it means to do arithmetic operations and other operations on those intervals. And so we're going to define it like this. For any operation circle, A circle B is going to be the set of all A circle B, little a circle little b, for A in the set A and B in the set B. But so for example, A plus B, we're just going to do exactly that thing. But these are sets with an uncountable number of elements. And so we have to find a better way of doing the calculation. And it turns out that for plus, for example, you can just take the lower bound of A and the lower bound of B and add those, and then the upper bound of A and the upper bound of B and add those. But in order to guarantee that the result can really contain all of the results that we would get from operating with any pair of elements, we have to do this directed rounding that I've denoted with these arrows. And so that means that one of the ways of doing that is to set the CPU to use round down mode or round up mode, and so it effectively does a calculation in infinite precision and then chooses a floating point number that is closest in that given direction to the correct result. And so talking with Jeffrey yesterday, there should be more efficient ways of doing this that we would definitely like to incorporate in the package. And that should be very easy because of the way that Julia allows us to, so we have an @round macro that does the rounding, and so if we just change that macro, everything should magically work, hopefully. Okay, so here's an example of, I hope you can see it, just, what are we going to do? I don't know. You used to be able to scroll down these these things. Now you can't. So, yeah. Anyway, so if we define, this is another notation for defining this interval, we're just printing out the interval, and then we can take sine, for example, of this interval. So again, we have to define sine, so this is a pretty large piece of work, to define all these functions. So sine of this interval should contain sine of x for any x in that interval. And there's actually, there's a series of people who have made a very nice test suite that you can adapt to your own interval arithmetic package. And again, Oliver Heinrich helped us to do this for our package. And so we have this really solid, how do we know that our system is correct? Because it satisfies this quite extensive test suite. Okay, so now let's, So now let's jump to Taylor series. So, so we have this suite of interval arithmetic in this validated numerics library, on one hand. And so now we'd like to think about functions. So functions are pretty important in mathematics or physics. And so one of the ways of, so sine x, for example, how would we evaluate sine x? Internally, what any implementation of sine x basically does in one form or another is use some kind of infinite series expansion. And so in this case, we're going to talk about Taylor series. So let's remind ourselves what a Taylor series is. So it's a way of expanding a function, f of x, around in the vicinity of a different point x0. And it looks like this. So it has this sum of powers of the difference, the distance from this point x0, an infinite sum of those, and the coefficients are given by the derivatives of the function at the original position. And so we've got this infinite sum represented by ... So infinite sums are bad news in a computer which can only do a finite number of operations. So what we want to do is truncate the expansion. So we can, of course, truncate the expansion in a naive way by just taking some number n of terms. But we don't want to do that because we want something that's guaranteed to be correct, that's guaranteed to include the true result. So we do actually have to take into account that infinite sum of terms. And we can do that by using Taylor's theorem with remainder. And so when I learned this at college, I thought this was completely useless. But actually, we're about to see that how to actually use it in a constructive way on the computer. So the Lagrange form of the remainder looks like this. So we're truncating the series at order 3. So we have a third order Taylor polynomial. And then the theorem says that the remainder has this form. So it's the fourth derivative of the function evaluated at some point, xi, times x to the 4th, where x is where I'm trying to evaluate this function close to 0. And what is xi? Well, we don't know what xi is. It's just the theorem says there exists a xi. And the xi is known to be in this interval between 0 and x, somewhere. And so the idea is, okay, so we want to have a bound on this value, this fourth derivative evaluated at xi. If we can have a bound on that, which means a lower and upper bound, in other words, an interval, then we'll actually be able to have a rigorous version of this sine function. So here's an example with sine. So sine has this third order expansion without the x squared term, and this error is the fourth derivative of sine. And we know, because we've done some calculus, that the fourth derivative of sine gets you back to exactly the same function again, sine. So we have to evaluate sine at this point xi that we don't know. But we know how to bound sine just for any value of xi, even anywhere in R, sine of that thing is between 0 and 1. It's between -1 and 1, sorry. So here's the interval -1 to 1. Right? So this is a mathematically correct statement. And now what we need to do is work out how to tell the computer that. Okay, so here is the actual calculation that we can do. So we're going to take a floating point number x, which is 0.5. So probably we actually want to make that an interval around 0.5. And then we can calculate this third order polynomial, which is just truncating the series. And we can ask, is sine of x, the true sine of x, is that inside this interval? And it is not. So we have not bounded you know, the thing in the correct way. So why? Because we have to take account of this infinitely long tail. And so how do we do that? The remainder term, according to this result that we've just found, is bounded by the interval -1 to 1 times this value of x to the power 4 divided by the factorial of 4. So we can literally write that in Julia, and that is the remainder. And then when we sum that with the original thing, then we get this bound that I claim is a rigorous bound for sine of 0.5. And indeed, it is. Well, indeed, sine of 0.5 is in there. That doesn't prove that it's a rigorous bound, but it is a rigorous bound. So that is the basic idea of how, so, you know, and yeah. Right, so, yeah, I should have actually said, so what does P look like? No, sorry. What does, oh no, we haven't got that yet, yeah. So that was where we were doing it by hand, right? I expanded the sine by hand in this Taylor series, and by hand, I bounded this error term. So there's a title there which says, what if we don't have, oh, come on. Oh. Why do these projectors not have a decent resolution these days? I mean, it's incredible.
You may be able to get higher resolution. Last week I was able to.
Right. Okay, that's a good point, yeah. Maybe I should do that. Well, no, I don't know how to do that. Okay. So what if we don't have these a priori bounds, or what if we can't do this expansion by hand because it's some complicated function? So what do we need then? We need a way to expand the function in Taylor series, and a way to bound the remainder using intervals, but that we can just get the computer to calculate with no interference from us. So we're going to use these two packages. So, oh yeah, so we've seen validated numerics, now we're going to see Taylor series. And so we're going to have, yeah, so how do we do that? So we can make, this is how to make, in the Taylor series package, Taylor series with, we can fix the type of the coefficients. So here, I'm just putting t as this type of interval with float coefficients inside. I'm going to fix that as the type of the coefficients of my Taylor series, and then do the expansion of that variable. So that variable looks like this. So it's a third order Taylor polynomial, and this O of t to the 4 just means that there's something else that I don't know about over there, and we can see that we've actually got intervals as the coefficients of the Taylor series. And then we need this fourth order, we need a bound of this fourth order thing. And so the way we're going to do that is like this. There's too much on this slide apparently for this projector. So we have this interval, and it turns out that the correct way to do it, if you think about it hard enough, so we had a big discussion about this yesterday, is to do this sine, so use this Taylor series package, generate this fourth order Taylor expansion, and but expand it, or sort of, in some sense, expand it around an x0, where the x0 is in fact this interval. And so the point is that so we don't really care now about the whole Taylor expansion. What we care about is the fourth order bound, the fourth order coefficient, which is an interval that gives us a bound on the fourth order derivative over the whole interval. And so, so that's the idea. So let's see what that looks like. Oh. Why is this not?
I have no idea.
Yeah, but I didn't want to actually evaluate that.
No.
Okay, let's actually get out of this. Yeah, we should have done that a long time ago. Let's get out of the. Okay. Yeah, here we go. So, so here's sine. So the blue curve is, sine of x. The green curve is the Taylor expansion to order n, where n is in this slider. And the pink is this rigorous bound that we're getting from this, this expansion using intervals. And as we increase n, so you may have seen this kind of manipulating saved math from a long time ago, but now we can add this, I guess they could have done as well, but this is all Julia now, so we're adding the... oh no.
Oh gosh.
Oh, for goodness sake. Where is that?
Here.
This is why Jeffrey brought his own projector yesterday.
Yeah, there it is. So, yeah, so as we increase the order of the Taylor expansion, the approximation of the polynomial, so this green curve is just the polynomial bit, and then the pink is this bound. It's a pretty naive bound. We could do better if we did more work. Shows you this rigorous bound, and indeed it contains the sine function. So again, we could do a better bound if we did more work. So, and with interact, thanks to Shashi who helped me the other day to fix my interact, you get this nice visualization. Okay. So that's the basic idea of the interaction between Taylor series and validated numerics.
So now what we will show it is that you have to be sometimes careful when you're integrating equations of motion. And the equation of motion that I will be considering is this very simple, ODE course 101 equation with this specific initial condition. Now, the reason to choose this is because you can actually solve it analytically. And if you notice it here, there will be a singularity. So if you approach t equal 1/3, you actually will blow up your solution. So why do we care about that? Because whatever you are using should somehow notice that this guy is there. You shouldn't cross that barrier somehow. And that guy, with this initial condition, is a non-exactly representable floating point. So you have to, it's sort of tricky. So we will be using ODE just as an example. Whatever. Then this is what you get as a result. So this is a straightforward code. Notice the warning, which is sort of tricky, whatever it means. But rather than only this warning, notice that the vector t, which actually prints your solution, which is right here, it is higher already than 1/3. So you have to be careful. I mean, you shouldn't have crossed that barrier. So how trustable is your solution? Well, in this case, it's simple because we have already an analytical solution. And if we have the analytical solution, we can simply check the result against it. Well, this is a simple check that indeed we have crossed the singularity. This is something which is related with the error, and this is actually plotting the solution. So it is not so clear here, but the crosses are the integrations from Runge-Kutta 7-8, and the round empty circles are the exact integration. And if you see the scale, which is a log scale, here it is 10 to the 6 or 10 to the 7, whatever, and here it is 10 to the 18. So you have missed it by a lot. And this is also shown here in this error, absolute error thing, graph. So can we do better? The answer is yes. So what I will be using first, it is this integration with Taylor series. So now we will be expanding the solution to a very high order, 18 in this case. We will be imposing some error bounds in the very last coefficient, which in a way impose that you are on the convergent tail of the series. And we will see what happens. And well, whatever it does here, this is the last point calculated, and you can see that it is wherever before 1/3. And this is nice. So how does it look? This is the way this thing looks like. So, I mean, by eye, you cannot really distinguish anything from here. And if you check the absolute error, well, I mean, the absolute error is growing. But it is 10 to the -6 for this integration instead of being 10 to the 18. Now, is this a validated solution? No. I mean, we still have an error which is sort of uncontrollable. Can we control it somehow? So what David just explained to bound this whatever function with a polynomial part and an interval bound is what we will be using here. So this is not the same function, but now let me emphasize, it is not the same function because sometimes you have to change your algorithms if you're working with intervals. But essentially it is. And it is now working with these intervals. And you see here the solution. Again, the last point is below 1/3. So that's sort of trustable. So here are some functions to plot it. The blue line here, it is the solution evaluated with the exact result, and the red boxes is actually a way of plotting that we are well within the bounds that we're predicting. So the takeaway from this simulation, it is that we can actually do much more with the intervals and other stuff than only bounding functions. In particular, we can get validated solutions of differential equations.
Okay, so to end, I'd like to talk about a package that I published recently called interval constraint programming. And so the idea is that we can actually think of intervals as a way of calculating with sets. So usually we're not used to calculating with sets. We have points that we move around, and if we want to think about a set, we have a cloud of points, and we see where that cloud of points goes. But we can, if we use intervals, then we can actually think about doing calculations with sets and do it in a rigorous way. And so we have this interval box, which is just a multi-dimensional version of an interval. So it's a Cartesian product of intervals. It's a rectangular or hypercubic box in n dimensions using fixed size arrays, which I forgot to put on the list of cool packages that we're using. So the point about Julia is, as usual, that we don't have to re-implement a lot of things that other people have already implemented. So we can concentrate on what we're interested in and just use their nice tools. So an interval box looks like this. This is a product of 0, 1 times 0, 1. That's going to be a square. So it's the set that is a square in the xy plane. Here's a matrix, just a normal Julia integer matrix. And I'm just going to multiply my matrix by this interval box. No. Multiply the matrix by an interval box, and you get a pair of intervals. And so if I can quickly draw what's going on, this is a classic matrix in dynamical systems. So we have this unit square. And when I multiply it by this matrix, this particular matrix, 2, 1, 1, 1, which has determinant 1, I get a parallelogram that looks like this, with area 1, and it goes up to 3, 2. And so what I've got out of this calculation is the smallest box that encloses the result of doing this calculation. Okay, so that's how we can do set calculations. So okay, we're getting an overestimate of the box. If we want a better estimate, we just split up this interval into some boxes, and then what we're going to get is a series of boxes that cover this set. So I don't have a picture of that, but that's called a paving. And so this interval constraint programming package uses pavings to represent sets in a rigorous way. So I'm actually going to just show you that very quickly. So this is what you do. This is what you write. Can we turn the lights down? This is what you actually write. At constraint, so solid torus equals at constraint, and just implicit, what do you call it? Inequality on x, y, and z in this case, 3 variables. So it works out automatically that there are 3 variables, and it turns that into something called a separator, which I don't have time to go into, but basically it's an actual piece of code that gets generated. So I can show you roughly what the code looks like with a simple example, x squared plus y squared less than or equal to 1. So if I call that C, that's a different kind of thing that's used in the separator called a contractor. Then what is the code of C that gets generated? It's this. So I actually talked about this in my metaprogramming tutorial on whichever day it was, and how to generate this code and what it really means in terms of I have a syntax tree and I'm generating this code to actually take information about this constraint that I'm in this particular set and propagate it down to the variables x and y. And this is, so I could just do bisection. So what I'm going to want to do is just find what is the set that satisfies these constraints. So it's called the feasible set. This is used in optimization. So this there was some inspiration from jump about this at constraint that looks like a jump thing, but it's a bit different. So then we just run this set inverse thing, and we pass it this separator, whatever that is, and this interval box, and we get this paving, which is a cover of the box. And then we can use GLVisualize in 3 dimensions, or just matplotlib in 2 dimensions to visualize it, and we get this. So what is that? It's a solid torus that I have cut by a plane. So it's actually the intersection of 2 sets in 3-dimensional space. So you can see that I actually, because we're doing Julia, I can literally just write, well, once I've implemented everything, I want the intersection of the solid torus and the half plane. So this is the intersection of 2 separators, which gives me another separator. And I just find, so I have a rigorous bound for the boxes that are inside this new complicated set and the boxes that are outside. And I can, for example, calculate the volume of that thing. Well, okay, I shouldn't have done that. But I can calculate the volume of it, and it gives me an interval bound for the rigorous volume of this set. So I think that's the end. So basically, yeah, so Julia is highly composable, and there's just these great packages that you can put together to do cool things.